Hello there, and welcome to this video on proof by induction. And in this video, we're going to be proving the result of the sum of squares. So, if you've done quite a lot of further maths, you'll probably recognise this result from summations of series. It's in the formula book, and you will likely have used it to show other results. And in this video, we're going to prove it from scratch using proof by induction, and that's something you can be expected to do. So here we go. So the first thing we need to do is show the basis case. Okay, and that is basically show that this is true for n equals 1. Okay, so let's show true for the case that n equals 1. So, when the left-hand side, we have n equals 1, we're doing the summation of square numbers from r equals 1 to n being 1. So what we'll be doing for that is just summing up 1 squared is 1. Okay, fantastic. And on the right-hand side, let's show that the formula works. So instead of n over 6, we'll have 1 over 6. Instead of n plus 1, we've got 1 plus 1. And instead of 2n, it's 2 lots of 1 plus 1. Let's work this through. So that's 1/6 of 2 times 3. So that's 1/6 of 6, which is 1. Okay, hurrah. We've reached what we want. So okay, so let's show for n equals 1. Okay, our second step, which I'll do in the bottom left. So step 2 is our assumption step. And for this, we are just stating that we want to assume true for n equals k. So assume true for any n equal to k. So we're going to use this later. So basically it's the step of saying, well, what can we use? We're going to use the assumption that this is equal to k over 6, k plus 1, 2k plus 1. Okay, so we're going to assume that that's true. For our induction step, which is step 3, and this is the big bit, so step 3, inductive step. It's helpful to write down a target expression. So what are we aiming for? Okay, so for our inductive step, we're showing true for n equals k plus 1. Okay, because if we've got our basis step, we'll show true for n equals 1, n equals k, and then show that it's true for n equals k plus 1, but true for all values. So our target expression, instead of n over 6, we're going to have k plus 1 over 6. And instead of k plus 1 in the bracket, we're going to have k plus 1 plus 1. Okay, so I'm just going to put that k plus 1 in purple, plus 1. And instead of 2n plus 1, we'll have 2 lots of k plus 1 plus 1. Okay, so just to highlight what that is, that's our formula that we're trying to prove, but instead of n, it's k plus 1. Okay, so let's do this then. So we've got the sum from r equals 1 to k plus 1 of r squared. And that is the same as doing the sum from r equals 1 to k of r squared, and then we're going to add on the k plus 1th term. So we're going to add on k plus 1 squared. Okay, so that's the first bit people find difficult. So this first bit, well, that's our assumption result. So we know that, and then what we've added on is the k plus 1th term. Okay, so we've added on k plus 1 all squared. So as I said, the first bit we've got from our assumption step. So I'm going to take the formula down from our assumption step. That is k over 6 k plus 1 2k plus 1. Okay, and then we're adding on our k plus 1 term, k plus 1 squared. Right, we now just need to keep our target expression in mind. So in our target expression, I've got a k plus 1 out the front, and over 6. Well, the first part of our expression here has a k plus 1 over 6, so we could factorise out k plus 1 over 6. The second part of our expression here does not have a factor of 1/6. So what I'm going to do in my next line is write that as, so let's copy the first bit out. So we've got k over 6 over factor. Let's write this as k plus 1 over 6 because I'm going to factorise that out. And then I'm going to write out the factor of 1/6 in the next bit. So in order to factor out a 1/6, I need to multiply by 6. So I've got 6/6. And instead of writing it as k plus 1 squared, to make it really clear what I'm going to factor out, I'm going to write it as k plus 1, k plus 1. Right, now what we can do is both of these terms have a k plus 1 over 6 and k plus 1 over 6. And if we think back to our target formula, we need to pull that out. Okay, so that's why we've made that decision. We'll worry about what we've got left over in a second. So this is equal to k plus 1 over 6. And then if we factor that out from the first part of our expression, so we're left with k lots of 2k plus 1. And in the second part of our expression, we're just left with 6 lots of k plus 1. Okay, great. So referring to our target expression, we've got the k plus 1 over 6. I just need to show that what we've got left gives us this k plus 1 plus 1 to k plus 1 plus 1. Okay. When in doubt, let's just expand. So this is equal to k plus 1 over 6. Let's expand out. We've got 2k squared plus k plus 6k plus 6. And let's tidy it up. K plus 1 over 6. 2k squared plus 7k plus 6. Okay, and now let's factorise that. For me, when I factorise, I use a cross to help me out. And then if I do the coefficient of k squared and the constant term times together, 2 times 6 is 12. And then put the coefficient of k in the bottom, 7. So I'm looking for a pair of numbers that multiply to give 12 and sum to give 7. That's 4 and 3. So that factorises 2, or I can rewrite that as 2k squared plus 4k plus 3k plus 6k is totally equivalent. And then we can factorise it as 2k, k plus 2, and the right hand side part is 3 lots of k plus 2. And then we can factor out the factor of k plus 2 from each of those. So we've got k plus 1 over 6, and then factor out the k plus 2. And that leaves you with the remaining parts, 2k plus 3. Perfect. Let's bring our target expression down. So copy my target. It's nearly there. All I need to do is rewrite k plus 2 as k plus 1 plus 1. And then rewrite the 2k plus 3 as 2k plus 2, or 2 lots of k plus 1 plus 1. And there we go. Okay, that's our result as required. We've done a lot of work. Don't forget that was only our third step. So we've shown our basis. We've shown true for n equals 1. If it's true for n equals k, then we've shown true for n equals k plus 1. Hence, it's always work for all natural numbers. Okay, so don't forget your wording of the conclusion step. So we're shown true for n equals 1. If true for n equals k, then true for n equals k plus 1. Hence shown for all natural numbers, so for all n greater than or equal to 1. Okay, hope that's helped. Thanks for watching.